Hello everyone, welcome to this video. In this video, we shall be talking about a question which appeared in December 2018 in CSIR-UGC NET exam consisting of 4.75 marks, right? The question is a characteristic number and the corresponding eigenfunction of the homogeneous Fredholm integral equation with kernel this are which of the following? So which among these four are the respective eigenvalues and the eigenfunctions, right? So let us get started. So they are we are given homogeneous Fredholm integral equation. So it would be something like this. The unknown, let us call the unknown function as y of x, that is equal to lambda, where lambda would be the characteristic number which we shall be finding. Then integration from 0 to 1 the kernel, then the unknown function dt, and because this is homogeneous, so here there is no fx, right? And the kernel is given to be this in the interval 0 to t and this in the interval t to 1, right? So let us try to solve this equation. So what do we have to do? We just break this integral from 0 to 1 to 0 to x and then x to 1, right? And now here the integration is being taken place over t, right? So this t is less than x in this case. So t is less than x here. So we shall use this value over here. So this becomes this, right? And the second integral from x to 1. So here t is greater than x. So that means we are talking about this, right? So we shall take the value of kernel to be this. So I've used it here. So this is my integral equation as for now, right? So to solve this equation, what we do, we convert this equation into the corresponding differential equation. So for doing that, we shall differentiate it with respect to x and we shall apply the Libiness rule. And what is that? It states that when you are to take the derivative of some function under the integral sign, what you need to do is you need to calculate the partial derivative with respect to that same variable x. So here it should be x, right? So with respect to x of the term uxt, whatever is inside this integral, plus then you have to take the upper limit over here, right? So ddx of b of x, and you have to substitute the value of t as the upper limit over here, right? Minus the derivative of the lower limit, that is ax, and you have to substitute that value of u over here, right? So this is our rule. So let us apply it over here onto the first integral. So what do we get? We get lambda integration from 0 to x. So first of all, the partial derivative of this whole term with respect to x, so it would just be t, right? It would just be t yt dt, this term, and then the derivative of x with respect to x, that is 1, and if we substitute in place of t x here, so we'll have lambda x minus 1 y of x, right? And the lower limit is 0, so its derivative with respect to x would be 0, so it is simply 0, plus lambda times the integration partial derivative of this term with respect to x. So what would be that? It would simply be this term, right? T minus 1 yt dt, right? And moreover, the complete derivative of this upper limit, that is 1 with respect to x, that would be 0, so next term is 0, and then the complete derivative of the lower limit minus of that, so it would be 1, and when you replace t here with x, you will get this term, right? So we clearly see that this term and this term being same, they cancel out because of the opposite signs. So we are just left with these two terms over here, right? So this is simple, nothing complicated over here. So let us differentiate it once more because we still have this integral sign and we want to get rid of this integral sign. So after differentiating again, what do we get? We get here y double dash x lambda, again applying the Libiness rule over here, we have to take the partial derivative of this term with respect to x, but there is no x, so this term would be 0, plus the derivative of upper limit, that would be 1, and replacing x t with respect with x over here, so 1 into x into y of x, minus the partial the derivative of lower limit, that is 0 with respect to x, so that would be 0 only. And let's come to the second term. The same rule we have to apply over here. There is no term containing x, so its partial derivative with respect to x would be 0, and the upper limit is constant, that is 1. The lower limit we have 1, right? So 1 into lambda x minus 1 yx, because we'll replace t with the lower limit, that is x. So you are left with this term. So when you simplify this, you'll get this. So this is a simplified differential equation of a second order. Now when you solve this kind of equation, you'll have two constants in your differential equation. So basically you need two boundary conditions to solve that constants. So how do we obtain these boundary conditions? So let us go to the value of y of x. Because the interval given to us is 0 to 1, this 0 to 1, that is why we calculate what is the value of y at this point 0. So y of 0 would be integration from 0 to 0. So this whole first term would become 0, and here it would be, let's see it in this term, when you replace x by 1, right? So this x by 0, then you'll have lambda integration from 0 to 1, 0 times something, so this whole terms again becomes 0. So 0 plus 0 is 0, so you'll have y of 0 is 0. So one condition we have is y of 0 is 0. Let's see another condition. What is y of 1? When we substitute y of 1 over here, so it'll be 0 to 1 t into 1 minus 1. So 1 minus 1 is 0, so this whole term is 0. And let's see what about the second term. So plus lambda integration from 1 to 1. If we take the integration from same point to same point, it will again give 0. So y of 1 is again 0. So these are the boundary conditions with us, right? So now the solution to this equation would depend on the value of lambda. So depending on whether lambda is positive or 0 or negative, we'll have different solutions. But we are interested in calculating the non-trivial solution, that means non-zero solution, right? So let us look at that. If in the first case, this is basically Sturm-Liouville kind of differential equation. So we'll discuss cases. So first case is when lambda is positive. So we take it to be k square, where k is not equal to 0, right? Because if k is equal to 0, then we'll reach at the second case. So when k is not equal to 0, we can take it as to be k square. So k square would always be positive. So our equation becomes y double dash x minus k square yx is equal to 0. So the corresponding auxiliary equation then becomes d square minus k square is equal to 0. So now you look for the value of d, it comes out to be plus minus k. So the corresponding solution y of x would be c1 e to the power kx plus c2 e to the power minus kx, where c1 and c2 are constants and which we eventually calculate. So let's use the boundary conditions that we have calculated. Y of 0 is 0, this gives c2 is equal to minus c1, and y of 1 is 0, so this gives us this condition. Now we have two cases, either c1 is 0 or the second term e to the power k minus e to the power minus k is equal to 0. If c1 is 0, c2 is 0, that means we obtain a trivial solution where y of x becomes 0, and we are not interested in this solution, right? So moreover, if this is not the case, then this should be 0. But this is also not possible because this is 0 only when k is 0, but we have assumed k to be non-zero. So this case is not possible. So we do not obtain any non-trivial solution when lambda is positive. Let us take a look at the second case. So let us assume lambda is 0. In that case, when lambda is 0, our differential equation, it reduces to, So it was a differential equation. It reduces to y double dash x is equal to 0. So integrating twice, we'll get something like this. So when you substitute the quantities over here, the boundary conditions, you will get a0 and b0 as well. So y is equal to 0 is the solution obtained in this case, which is the trivial solution and not required. Next is the case when lambda is negative. That means we take lambda to be minus k square, where k is non-zero, right? So our equation in that auxiliary equation in that case becomes d square minus of minus k square, that is d square plus k square is equal to 0. So we have d is equal to plus minus iota k, and the solution in this case is c1 cos kx plus c2 cos kx. So let us calculate the constant c1 and c2 using the boundary condition. Let us substitute y of 0 is equal to 0. So in this case we get c1 is equal to 0 because this is 0 and sine of 0 is 0, so c1 becomes 0, and let us substitute y of 1 is equal to 0. So we obtain this expression. Now again we have two cases. The product of two terms is equal to 0. That means either the first term is 0 or the second term is 0. If c2 is 0 and c1 is 0, that means we again obtain a trivial solution not required to us. So let us see the second case. Sine of k is equal to 0, and you know sine is 0 at which quantities? N pi, where n is what? Plus minus 1 plus minus 2 and so on. So our k is equal to n pi. So we obtain k and thereby lambda. So what was lambda? Lambda was minus k square. So lambda is equal to minus n square pi square. So this is our eigenvalue which we are looking for. And what is the solution? Here c1 is 0 and c2 is arbitrary. That means it can take any value. So we reach at our solution, non-trivial solution. What would be that? It would be for all those values of lambda where it is negative. That means we have minus n square pi square, where n is any integer, right? Not equal to 0. It could be 0 also. Not equal to 0. If it is 0, we have the trivial solution, and c2 is arbitrary. Therefore, the solutions which are known as the eigenfunctions, they become c2 sine n pi x, right? So this is arbitrary. So now let us look at our options, or let us look at the values when n is 1. Let us assume c is equal to, c2 is equal to 1. Why I'm doing this? Because I want to be consistent with the options given in the question. Let us have a look at the options. So these are the options. Let us look at which options are correct. We have lambda is equal to minus n square lambda square. So this is not possible, this is not possible. Let's look at the other cases. So when n is equal to 1, we have lambda is equal to minus pi square, and the corresponding eigenfunction would then become c2. Let me take it 1. So it would be sine, what is n? N is 1 pi x. So this is that. For n is equal to 2, we have lambda is equal to minus 4 pi square. Why? Because n is 2, so 2 square is 4, and then y of x would be sine 2 pi x, right? For 3 it would be this, and so on. So let us look at our options. For minus pi square it is sine pi x, and for minus 4 pi square it is sine 2 pi x. So this option is correct and this option is also correct. So we have option A and option D as the correct options. Well, that is it for this video. Thank you for